This section looks at the planes in a vector space and asks what happens to them under translation, intersection with each other, and images under linear maps. Then it narrows to the translates of one fixed subspace and finds that set is itself a vector space. The definition: for a subspace in and any vector, the set of everything in N shifted by that vector is called the coset containing it, or the affine subspace through it parallel to N. These are the general objects section 2 wanted to call planes. First property: if one vector lies in the coset of another, the two cosets are the same. Second, any two cosets are either identical or disjoint. This is the equivalence relation of Chapter 0 in a special case, with two vectors equivalent when their difference lies in N. More of them. The intersection of any family of affine subspaces is either empty or an affine subspace, and the set sum of two affine subspaces is again an affine subspace. A linear map carries an affine subspace to an affine subspace, and the preimage of an affine subspace is either empty or an affine subspace. Translation itself is not linear, since it carries 0 to the shift vector rather than to 0. But it does carry affine subspaces to affine subspaces. A linear map followed by a translation is called an affine transformation. Now fix a subspace and look at the set of all its translates. The book's example: if it is a line through the origin in 3 space, that set is all the lines parallel to it. What is worth noticing is that these parallel lines form a vector space in their own right. The set sum of any two is another line in the family, and so is a non-zero multiple. The translates fiber the space, and the set of fibers is naturally a vector space. Addition is set addition, and scalar multiplication is the set product, with only multiplication by 0 needing a separate stipulation, namely the subspace itself. The natural map, sending a vector to its coset, then preserves both operations. A theorem saves the work of checking every law. If a set carries two vector-like operations and some vector space maps onto it preserving them, it is a vector space. So the quotient space is a vector space and the projection is a surjective linear map. The main theorem here: if the null space of a linear map includes a subspace, the map factors uniquely as the projection onto the quotient followed by a linear map. And if a subspace is carried into itself, there is a unique matching map on the quotient.